For thousands of years before the arrival of modern technology, humanity has wondered about the existence of planets orbiting other stars. It wasn't until 1992 that we obtained strong evidence of their existence. Now this might beg the question, how do we find these planets anyway? It seems like an impossible task. From our vantage point on Earth, distant stars appear as nothing more than pinpoint light sources. And even if we could resolve them, there's the problem of the planet being drowned out by the star's light. However, for the last 30 plus years, 5 main solutions for finding exoplanets have emerged: transit, radial velocity, microlensing, direct imaging, and timing. Each of these methods have their own fascinating tricks. This will be the first of a 2-video series where we explore these methods. In this first video, we'll explore transit and radial velocity, and in a future video, we'll explore the remaining 3. On Earth, we experience solar eclipses every so often. This is a phenomenon where the moon appears to partially or totally block the sun from the Earth's view, creating a shadow. A much less spectacular event is when either planets Mercury or Venus pass in front of the sun. This phenomenon of a celestial body passing between the observer and a larger body is called a transit, and we can also indirectly observe this occurrence around other stars which may have planets orbiting them. The principle here is to monitor the apparent brightness of the star and watch for periodic dips in its brightness. You can't actually see the planet in front of the star since it's just too small. Look how small Mercury looks even from Earth. But seeing a periodic dip in brightness can indicate that there is, in fact, a planet orbiting that star. If there are several planets, these dips in brightness would be added to each other, and scientists can use algorithms to isolate these transits and attribute them to particular planets like they did for TRAPPIST-1. This method works especially well for stars that have very large planets orbiting extremely close to them. These planets are called hot Jupiters, and I have a full video explaining them in more detail if you're interested. With a big enough planet, the transit can even be detected by amateur astronomers. Here's a light curve that I obtained with my own telescope of a hot Jupiter orbiting a star. These hot Jupiters also tend to have very short orbital periods, mostly orbiting in only several days, some even in mere hours. For this reason, planets that have quick orbits close to their stars are the easiest to confirm using this method. One very unique advantage of the transit method is that it allows astronomers to analyze the atmosphere of the target exoplanet. This is done by using spectroscopy, which is a method that allows for the unique identification of chemical elements solely based on how they interact with light from the star. Astronomers record the spectrum of a star when the planet is behind, and then measure it when in front. Taking the difference between these two spectra leaves us only with a spectrum of the planet's atmosphere. Because of this, a large number of transiting exoplanets, mostly hot Jupiters, can have their atmospheres characterized in great detail. For example, the hot Jupiter HD 189733b is about 65 light-years away, and gases such as carbon monoxide, carbon dioxide, methane, water vapor, and silicates have all been detected. Another more recent example is the TRAPPIST-1 system, although these planets are not hot Jupiters. But with the powerful James Webb Space Telescope, astronomers have been able to gain insight on the first 3 planets' atmospheres. We now know that, most likely, Planet B and C have very tenuous atmospheres, if any at all. The transit method also allows astronomers to learn more about the planet's orbit, specifically its radius, inclination, eccentricity, and so on. While the transit method is a very powerful tool for detecting exoplanets, like any good method does, it also has its drawbacks. Starting with perhaps the most obvious being that not every star system is oriented in the correct way to Earth. Any star systems that are not edge-on, for example, are completely invisible to the transit method, meaning it misses out on many systems. It is estimated that about 90% of all exoplanetary systems are not detectable using the transit method. Another less obvious drawback is that this method is particularly prone to false positives. Remember that the main principle is to observe a star and watch for periodic drops in its brightness. There are other phenomena in space that can cause this to happen. One example is that the target of interest doesn't have a planet, but rather is an eclipsing binary system. This is where one member eclipses the other from the observer's vantage point, causing periodic variations in the target's brightness. Other possibilities include stellar activity, variability, and other properties about the star. Despite these and other potential drawbacks though, the transit method is evidently a very powerful tool for detecting exoplanets, and we'll see that the radial velocity method has its own details and applications. On a macro scale, we see that smaller bodies tend to orbit bigger bodies. The Earth and the thousands of other objects in our solar system orbit the Sun, meaning they revolve around it. However, the idea of an object orbiting another is actually a two-way property on the physical level. Take the Pluto-Charon system, for example. Charon is Pluto's moon, but this is an extreme example of what happens when two similar-sized bodies orbit each other. Pluto and Charon orbit around a particular point above the surface of Pluto called the barycenter. Suppose we have two bodies that orbit each other, A and B, which have identical mass. The barycenter is then perfectly in the middle of the orbit. Then, as you increase the mass of object A, the barycenter will move closer and closer to the core of A. But here's the important thing. The barycenter will never perfectly be at the core of object A. What this means is that there will still be some movement on A's part, a wobble if you will. We see this extreme example with the Pluto-Charon system, but with sensitive enough instruments, this can be detected with distant stars. They can appear to have some velocity forward and backwards over some period of time. This velocity is called radial velocity, and it's the main focus of this method, as the name implies. In the same way that Charon causes Pluto to wobble, a planet that orbits a star will cause the star to wobble ever so slightly. This change in velocity is detectable with modern spectrometers, which observe a Doppler shift of the star's light. Based on the period of this shift, astronomers can conclude that there must be a planet orbiting the star. The radial velocity method is especially helpful with nearby, low-mass stars, and red dwarfs fit this criteria. This is actually how Proxima b was discovered, using radial velocity measurements from Proxima Centauri. Some physics allow astronomers to figure out properties of the planet, such as its minimum mass. However, there are of course some drawbacks to this method, one of which being that it can tell us nothing about the planet's atmosphere. Remember that with the transit method, it's the act of transiting that allows scientists to analyze the atmosphere of a planet passing in front of its star. With radial velocity, however, observing the wobble of a star will not provide any information. Another issue is that stellar activity, such as flares and shifts within its magnetic field, can disturb the spectrum of the star, leading to false positives, although there are techniques to account for this activity.